Hey everyone, welcome to the OpenUSD Insiders live stream. Particularly, this episode is called Accelerate Computational Engineering and Robotics with NVIDIA Warp. We're also going to touch on Newton. I am thrilled because we have some very special guests from our team here, and all of you watching out there are also very special guests because we invite you to send your questions and comments in the live chat. We don't often get these three people here together, so this is an amazing opportunity to really dive in and ask your questions. As many of you know, I'm Ed Marr. I'm the community manager for NVIDIA Omniverse. If you haven't heard, and as you can see on the screen, Warp just crossed 10 million downloads. 10 million. And if you're wondering what you can do with it, well, one of the use cases that I shared on LinkedIn from one of Miles' teammates is that you can actually run Doom on it. But we're gonna talk about a lot of other deeper topics in that. But you can run a lot of things directly on the GPU. Today we've got Miles with us, we've got Mohammed, and we've got Boomi. They're going to introduce Warp and Newton, walk through the latest features, share some code. They're going to also highlight some of their favorite community projects and stories they've seen of people leveraging Warp. And as I mentioned, most importantly, they're here to take your questions. So the more on topic your question is, the more likely we can kind of talk about it live and show it on the screen. All right, so I also invited a couple people to send us questions beforehand, so I'll hit those later, and we'll cover news, which we have definitely some great news to share at the end of live stream. All right, so let's get right into it. Let's start off with some introductions. Boomi, you're going to join us at the end, but before you go, tell a bit about what your role here. You're going to be helping out a lot in the chat today, but what's your role in NVIDIA?
Yeah, definitely. Thanks, Edmar. Hey, everyone. Nice to meet you. We're super excited to showcase this live stream today and showcase how Warp has crossed 10 million downloads. It's phenomenal, and we'll showcase how it's used by different developers and how you could use as well, and hopefully inspire you all as well. I lead product marketing for CAE at NVIDIA. I've been here for 5 years, and in my career, I've worked on different roles. I'll be helping Miles and Mohammed here to make sure the ecosystem stuff goes well, that they're going to showcase how the adopters are using Warp, as well as pop up all the questions you guys have in the chat so we can have some live discussion at the end.
Awesome. All right. Thank you so much for helping us. And Miles, it's so awesome to have you. I just saw you really briefly at one of our events. It was so good to see you live, but great to have you join us on a live stream. Why don't you, for people who aren't familiar with you and your background, your role here, why don't you share that?
Yeah, sure. Thanks, Edmar, for having us. I am a director of engineering in the simulation technology team. So I've been working on physics simulation at NVIDIA for quite a long time. Worked on physics, worked on things like Flex, robotics, Isaac. So anything to do with physics simulation. And yeah, we're really happy to celebrate this 10 million milestone this month. It's pretty amazing. We never thought we'd get this far. And it's in large part due to the community's contributions, right? How much they've built with Warp, all the PRs, all the bug fixes, all the performance and benchmark problems they've sent us. So yeah, I just wanted to say a quick thank you to the community for helping us get to this milestone.
That's awesome. Well, thank you so much for being so involved with the community. And you have your partner here, Mohammed. Hey, Mohammed.
Hey, Edmar. How's it going?
Great to see you. So tell a bit about your role here at NVIDIA.
Yeah, for sure. So my name is Mohammed. I'm a product manager for Warp and Newton. So I'm here to tell you all about how the community and our developer ecosystem have used Warp to reach this exciting milestone alongside what Miles have to tell you about what Warp is and give you a little bit of background of the origin story of Warp.
Okay, cool. All right, so everyone buckle up. Remember to get your questions and comments in. Boomi, I'm going to bring you down. We'll bring you back up a little later. Thank you for the intro. Okay, Miles. So yeah, for people who have never heard about Warp and aren't familiar with it at all, what is it, and yeah, how did it all begin?
Yeah, thanks, Edmar. I think it'd be nice to give a little bit of the origin story for Warp. I don't know if we've ever really done that. We usually just talk about what it is, but not why it sort of came about. So maybe I can start with some background. And I've been at NVIDIA I think around 15 years now. Like I said, I've been working on simulation with physics, Flex, and other things. My first job when I joined NVIDIA was to port physics to the PS3. So I was working on like PlayStation 3 development. and integrating our simulation tech into games, doing things like real-time cloth, real-time fluids, all sorts of simulation. And, we did that for around 10 years, working on real-time simulation. And you can imagine that over that time, we built a lot of technology, right? We wrote a lot of CUDA code. We wrote a lot of data structures and algorithms for simulation, collision detection, solvers. And, we integrated those into all sorts of applications. But it wasn't until about 2020 that things started to change significantly. And simulation kind of became more interesting outside of just games. AI was coming up. And in particular, in 2020, differentiable simulation was a really hot topic. This was everyone was hyped about differentiable simulation. I had technical artists, I had roboticists all coming to me and saying, why isn't my simulation differentiable? You have to build us a differentiable physics engine. And I was also super excited by this idea that you could connect physics with AI through differentiable simulation. And so I started looking into it, and it was pretty clear that back then, 6 years ago, the tools were really lacking. There just wasn't something, there wasn't a thing we needed to build simulation in a differentiable way. So, back then, if you wanted to write a differentiable program that ran on the GPU, you didn't have that many options. You had basically PyTorch, TensorFlow, the kind of DL frameworks, right? That was your standard way to do it. And those frameworks are great for deep learning, but they're really optimized for dense linear algebra, tensor operations, everything that you do inside neural networks. And if you look at physics code, it's actually almost the exact opposite, right? It's branchy, it has lots of conditional logic, it has sparse computations, structured data. It's really not a great fit for those DL frameworks. And so I was trying to express all of our algorithms that were built up over that time in a sort of tensor-based framework. And really, it was just incredibly difficult to do that efficiently. And so, just to give an example, I think it's nice to kind of really make that concrete. This is a routine that you would find in any physics engine, right? This little function computes the closest point in space to a triangle. And you can express this in a DL framework, right? So the left-hand side is what it would look like in PyTorch. And it's quite concise, but there are a few sort of subtleties here that make it hard to reason about. And in DL frameworks, you kind of always have to think in terms of large batches, right? So you're operating on 1 million triangles and a million points at once, and so you end up with these slightly unusual things like sum minus one, right? Why do I have to have that in this routine? You have your conditional logic that becomes things like select and statements, these torch-aware statements. And so, syntactically, it's really not that elegant, I would say, or natural for someone coming from a academic or traditional simulation background. The other point here is that it's usually less efficient. Each of these lines, roughly speaking, corresponds to a kernel launch in PyTorch. And so writing it this way, is typically less efficient than how we would have done it traditionally in CUDA or C++. I think the way that we really wanted to write it was more on the right-hand side. This is a very imperative traditional way of writing this kind of function. You think about one problem at a time, one point, one triangle. You compute a few dot products. You have your conditional logic and early outs. So you actually have a proper if statement. You can early out if you find that you've found the closest point. And so this is really just more natural, I would say, especially if you're coming from this background that I had. And really, this looks just like the textbook algorithm. You could pretty much copy paste this out of a textbook. And so we wanted a way to write it like this. And this is really what led us to a research project we called DFlex. DFlex was a differentiable version of Flex that I created internally. That was essentially a sort of rudimentary compiler for Python that would take a kernel like this and turn it into a GPU code that was differentiable. And after a few years, we realized that this was useful beyond just physics code. We realized we could actually write any kind of CUDA kernel with this framework, and we started using it all over Omniverse for lots of different extensions and geometric processing, different types of spatial operations. And so we renamed DFlex. It sort of grew up, and Riv, who's our VP, came up with, I think, a pretty nice name, which is Warp. And the idea with Warp is that, it's a Python package, first of all, right? So you pip install it. You can import it into your environment and then write your function in a slightly special way, right? So you write your function with your inputs annotated here. You decorate it with this little WP kernel decorator. And you write your function, and it looks a lot like HLSL, like a high-level shading language, or sort of standard kind of C code, or Python code, I guess. Then you can launch that function on the GPU or CPU, right? So Warp kind of supports both paths. And you launch your function, you tell it how many threads you want, you give it your inputs and the device to run on. And it takes care of all of the just-in-time compilation, and essentially lets you develop in Python with the performance of CUDA. And so that's, just from a developer productivity point of view, even putting aside differentiable simulation, this is a great way to write kernels because it's all in Python. It's all you get that benefit of just being in the Python ecosystem and all the great frameworks that come with it. But with Warp, we really wanted to pull in all of those data structures and algorithms that we built over that 15 years of working on simulation, and so we expose those as first-class citizens in Warp as well. So that's things like, our vector math libraries for quaternions, our data structures for mesh processing, sparse volumes, things like hash grids for point cloud processing. We kind of had built those for our physics engines like PhysX, but they were kind of locked away inside the engine. And you could only sort of use them if you created like a rigid body or something. But with Warp, we said, okay, we should actually expose those, make those the kind of primitives that users have access to, and then they can compose them the way that makes sense for them, right? So I think that was a big shift for us, was actually exposing the underlying data structures as the API itself. And of course, differentiable programming is still a core part of Warp. And when you write these kernels, you get also the backward version of them, so you can plug gradients from the simulator back into your deep neural network. And finally, Warp is open source. So, this was a really nice change in the last few years, that now it's a fully open source library, and we've had amazing contributions from the community, like I mentioned. So just to kind of recap, like the timeline, I think it was around 2020, we had this research prototype internally. Probably no one here would know what DFlex is. It was really just a research paper at that point, but it was very much a PyTorch centric thing. It was like an extension for PyTorch. A year later, we realized that this is more useful just beyond pure like robotics sim, and we generalized it and made it NVIDIA Warp. We made PyTorch optional. And even back then, it was still very small, right? Maybe a couple of thousand downloads a month or something. And in 2024, we launched 1.0. So we spent like actually 3 years building up to like 1.0. So it had a long time to stabilize. And now we have the open source release. We have monthly release cadence on GitHub across all the major platforms. And today we're up to Warp 1.17, and we have 80 plus contributors, around 1 million downloads a month, which is incredible. And Warp is really the foundation for a lot of our work on Newton and other technologies at NVIDIA. And a fun fact is that I think a lot of folks would have been looking at DLSS 5 in the news the last week, the amazing results there. And an interesting fact is that DLSS actually uses Warp in its training. So it uses differentiable image processing kernels written in Warp during training. So yeah, they were one of our first users, and it was really a surprise to me because we wrote it for physics, right? But they started using it for image processing. So yeah, that was a nice surprise.
That's wild.
Yeah. So yeah, that's kind of the origin story. I thought I could now just give a little bit of a technical deep dive, just talk a bit about some of the features for folks who aren't so familiar. And then Mohammed's going to talk a little bit about use cases and some of the cool applications. But like I said, Warp's a Python package. You pip install it. It has 3 main modules. The core namespace, Warp, gives you all of the built-in primitives like the math and geometry libraries. And we have a couple of very, more domain-specific, let's say, modules in there as well. So we have warp.fem, which is a framework for partial differential equations. This is a really nice way of defining, like a fluid flow problem or any kind of PDE problem in a high level that looks a lot like your kind of math notation, but then it's going to take that and build this like sparse linear system and the right hand side, and from there you can solve it. And warp sparse is typically how we do that. So warp sparse is a sparse matrix library that's tailored to the kind of problems that come up in physics. In physics, you typically always have some kind of block sparsity, and that's really what warp sparse is designed for. But it's also interoperable with things like cuSparse. So we generate CSR matrices you can hand off to cuSparse if you want to. But yeah, these are just some of the examples in the SDK that we ship. So lots of great examples to kind of get folks started. The data model is in Warp a little bit like, if you're coming from PyTorch or JAX, you'll be familiar with it. It's we use a WP array type to manage memory. This is kind of the equivalent of a torch tensor. And within the array type, we have leaf types, which would be things like your small Vec3s, Vec4s, Mat33s, quaternions, all of the types that you expect to, are so common in simulation and geometry processing. And this is kind of one of the things that makes Warp specific to those kinds of domains versus Torch, which is, very general. Like Torch is, just thinks about scalars basically. And so we have all these built-in types and the routines on them. One of the things about Warp that we try really hard is to improve the interop of Warp with other packages, right? We're not trying to, replace Torch or JAX. Those libraries are great, and they're absolutely, I think, the best at what they do for deep learning. And so we put a lot of effort just to working and playing nice with them. So that can be like zero copy interop of data, sharing streams, even doing like graph capture across those frameworks.
Yeah, Miles, you have a quick question from Maitri about can Warp work in different frameworks? I think this is quite aligned with what you were talking about. You talked about like PyTorch, JAX, NumPy. What are the other type of frameworks Warp can integrate with, interoperate with, native or not, Python or not, basically?
Yeah, I think there are other deep learning frameworks. There's one called Paddle as well. Paddle is probably less well known, but we do have interop support for it. Pretty much anywhere that you have support for this array interface or CUDA array interface or DLPack protocol, this is kind of like the glue that binds all these things together. And really, these protocols are just a way of describing a tensor. So they are essentially just a pointer, the shape of the tensor, and some strides. And that's what warp arrays are. And so we can convert to any of these protocols, and all the frameworks support different variations of these, right? So I think for TensorFlow, they support maybe like DLPack. JAX, I think, leans heavily on DLPack. Torch supports CUDA array interface. We kind of support them all, and that means we can go like to all of them.
Mhm.
And for non-Python frameworks, I'll talk a little bit about that soon, but again, there is a C version of like this array interface that we can convert to. So if you've got a C library, maybe it's got some Python bindings, then you can construct one of these and pass those arrays in. So yeah, that's one way of doing interop.
Okay, very interesting. One of the use cases I've seen, especially with JAX, where people are like doing all the machine learning algorithms and like large tensor processing, whenever they want to do customization through JAX FFI, they usually had to go like lower to CUDA, C++, and now with Warp, they could actually do it at a more convenient level without losing much of the performance. Especially in like, as you said, like in physics, like when there are like AI physics applications where that you want to, have a specific like kernel written with a lot of conditionals and all that, instead of going to CUDA, you would go to Warp. Is that something that you see like more and more being supported?
Yeah, definitely. So we have this, this way of taking a Warp kernel and you can wrap it as a JAX op. So we have like WP JAX kernel or something like that. You pass it a kernel, a Warp kernel, it gives you back a JAX op. And then that JAX op can go into any of your like JAX JIT or anything like that, which is, really convenient. So the sort of boundary between the two is actually pretty small these days. And yes, like you said, like there are usually some parts of your pipeline that are just not well suited to tensor frameworks, right? Often you'll have your MLP or transformer, and then you'll have some, more complex logic. Maybe it's like pre or post processing, maybe it's simulation, but it's, something that's hard to express in JAX potentially. It's quite convenient, like just to write a small kernel, wrap it in a JAX op, and make it part of your pipeline.
Yeah, and then the differentiate the basically autodiff also we contribute to JAX autodiff as well, right? The same
That's right.
gradient.
Yeah. So first order gradients will flow backwards in the in that graph as well. And so obviously this is one of the approaches we took with Majoko Warp, right? So Majoko Warp for GDM, obviously they care a lot about JAX, and all of their the top level of their stack is in JAX. And so we put a lot of effort into making the Warp JAX interop work really well.
Amazing. Thank you.
If anyone's wondering too, we had a couple questions there about the link. So I'll put it on the screen because it's a pretty easy one to remember. github.com/NVIDIA/warp. And thanks to our producer, Amelia, who's sharing these links in the chat. But a lot of congratulations and people impressed and who really love Warp in the chat, including, I see Omniverse Ambassador Scott Dempsey is here. And he said Warp is amazing. And it also offers big congratulations on 10 million downloads. Very cool.
Nice. Thanks, Scott. Yeah, I know Scott quite well from some of our events that we've
he's a huge fan. I have to tell you, he's great. Whenever he sees a great use case of Warp in the community, he'll message me, "Oh, you got to share this with Miles." And of course, I share that with the whole team, including Miles. And so yeah, we love seeing the use cases. And I wanted to ask you too. Maybe we'll get into this a little bit later, but it'd be really fun to hear about the different things you have all been surprised about by seeing that maybe you didn't expect Warp would be leveraged for. But we can talk about that in a little bit when you're finished with this.
Yeah, I think Mohammed has an amazing selection of some of those projects. Amazing. So we'll definitely get into that. Just to sort of finish up our deep dive here on the sort of a technical level, I talked about the data model or the data types. The other side of that is the execution model. And for Warp, we don't try and reinvent the execution model. We inherit the execution model from CUDA, but we do try and make it a little bit easier to use. And so in CUDA, you would have to break down your problem into CUDA blocks. In Warp, we do that for the user automatically. So the user just has to, or developer just has to pick the size of an n-dimensional array of threads. So some kind of grid, could be 2D, 3D, 4D, and we handle the mapping to blocks under the hood. So this just makes it more convenient for the common case that you don't really care too much about the mapping to blocks. But it is a very sort of SIMT style syntax with, you know, conditional logic and everything supported inside the main kernel. We recently, I think last year, added tile-based operations. So this is for operations where you want more than one thread to cooperate. So maybe you want to compute the sum of like part of an array or something like that, or compute a matmul using a bunch of threads. And the tile-based API allows you to do that through a pretty nice high-level abstraction that is backed by cuBLAS, cuRFFT, and all the sort of math DX libraries. And so the kind of unique thing about Warp is that both of these programming models can coexist in the same kernel. So we have a way of like switching between single thread to cooperative thread approaches. And some folks might have seen things like Qtile have come out recently. This is very related and also related to things like Triton. I can talk more about the kind of overlap there, but Warp's approach is, you know, quite unique in the fact that you can kind of combine these things at a fine granularity. I mentioned auto diff. So one of the key things about Warp is that when you write those kernels, they're differentiable. And so typically you would start with the tape. This records all of your kernel launches, mem copies, any kind of operations that you're doing. And at the end, you compute some loss function or loss value, and you can run that tape backwards. And this is essentially doing back propagation through all those, you know, kernel launches, computing gradients of your inputs with respect to your inputs. And so this is one of my favorite, like probably one of the earliest examples we did with differentiable simulation, just showing a ball trying to hit a target, and the goal is to optimize the initial velocity of the ball such that it, you know, lands on the target after half a second. And because this was written in Warp, we could automatically just write the loss function, which is the distance of the ball to that target, and it's going to compute the gradients with respect to the initial velocity. We use some off-the-shelf optimizer, like, you know, just gradient descent, or, you know, LBFGS, something, or Atom, something like that. And you can pretty quickly get to a trajectory that works, that hits the target. Even though there's some, you know, contact here, there's friction here, we can optimize through those pretty well for this kind of example. So, and like Mo said, we support custom gradients, and the gradients can flow back to PyTorch and JAX, so that you know, those gradients can be used to update neural network weights, for example. In terms of data structures and algorithms, these are really, I think, often these are the things that really draw people to Warp, right? So they might want to compute like the closest point to a mesh, right, to create an SDF. They might want to do some neighbor finding in a point cloud. They might want to like find all the overlapping elements in some region. And we kind of provide all the data structures for that. And so these are just some examples of like, this is using the hash grid. So using the hash grid, you can find all your particle neighbors, you can compute some forces, and create these kinds of like DEM style particle simulations pretty quickly. I think like both of these, just over 100 lines of code. So, you know, it's really, you can express this type of simulation really concisely just using some of these built-in data structures.
Very cool.
Compilation pipeline is also a little unique for Warp. You know, I'm not a compiler guy, I'm a physics guy. And so when we first wrote Warp, I didn't really want to use LLVM or some like, you know, big complicated compiler stack. The idea was that we would look at the kernel code in Python, we'd traverse the abstract syntax tree and generate C++ directly. So we actually use C++ CUDA as our intermediate representation. And it turns out this has some pretty nice benefits. The first is that we can use, you know, everyone else's compiler for compiling, right? So we can use NVRTC, which is NVIDIA's runtime compiler, to just directly compile the C++ CUDA. The other benefit is that all of that C++ CUDA that we created over the last few years can be sort of hash included directly into the mix, right? So we didn't have to rewrite it in some other language. We could just hash include our math library directly. We generate our PTX and OBJ, and then we launch it from the Python process. And I think you mentioned Doom at the start. Edmar, one of the guys on my team, Chris, recently ported Doom to run on Warp, which is pretty surprising. I mean, Doom runs on everything. Obviously, it can run on like calculators, but this was one of the workflows that he used in that work, which is, the problem we're trying to solve here is that if you look at especially in robotics, there's this huge gap between training a robot policy and deploying it on a device. So everyone trains in Python, trains in PyTorch, and maybe Warp. But when you go on the robot, it's an embedded device. It's low power, right? So you can't run all that like heavy Python stack. And so the problem is, how do you kind of go from training environment to deployment without rewriting all of your code in C++, which is pretty much what people do today. And so this is a new feature we've been working on that allows you to essentially capture a series of launches. And we do this pretty regularly in Warp already, just for performance. Once you've done that capture, you can save it out to disk. And so you save a .wrp file. And this includes all the information about the kernels that got launched, the memory that was used, and it's a binary file that you can then load and run from C++ without any like Python in the mix. So pretty efficient and useful way to just close that gap between training and deployment.
Yeah, we actually got a pretty timely question here that Mohammed noticed. This is coming from Michelle on LinkedIn. From physical AI teams moving from simulation to real-world deployment, how do you see Warp fitting together with Isaac Sim and Isaac Lab? So,
yeah, that's a great question and very relevant to what I'm talking about here. For Isaac, we have a framework called Leap, LEAPP. And Leap is a way of essentially taking a Torch or NumPy or any kind of array-based program, serializing it to Onyx, and then running it on your robot. So they're building like deployment tools already for this kind of workflow. Leap is going to be integrating this work as well. So soon you'll be able to, from Isaac, use Leap to serialize out an entire PyTorch, NumPy, and Warp program to a single Onyx file, basically, that you can deploy on the device. Yeah, so it is being integrated into the Isaac workflows as well.
Yeah, I just want to add to what Matt's saying about like whether you're using Warp in a case of like, let's say, sensor processing. So you're receiving images or sensor data on the device, and you have kernels that you've written in your development phase to prototype something and run in simulation. Now you want to run the same kernel to process real sensor data. You could actually, through this pipeline, you can bring a code that you've written in Python and deploy it in a non-Python environment, which is your deployment. Or you can go even further. Let's say you're going to talk a little bit about Newton today. You have a basically inverse kinematic routine from Newton that you've used. Now you want to use it on the controller on the device. Then that's also something you could use this workflow to deploy the same IK in simulation to the real world.
And here's another question that Boomi just flagged that would be good to talk about right now. Also coming in from LinkedIn, can we make native C++ or CUDA code inside Warp Python function?
Yeah, that's a great question, and definitely one of the advantages, like I mentioned, about using C++ as the intermediate language. So in Warp, we have something called a Warp native func. So inside a Warp native func, you basically just have a blob of C++ CUDA snippet, like a string of the piece of CUDA you want to include. So this is a really useful kind of escape hatch, right? So maybe you want access to some really low-level CUDA intrinsic. You can just basically include a small string that encodes that and reference it directly from the rest of your Warp program. We are also, so that works really well for like small kind of snippets. We are also going to be opening up the compilation pipeline a little more, so you could add like whole headers and things like that into the JIT.
Fantastic. Let me see. Here's another one, I think, that she's flagged. Let me see if I can find it here. I think it's this one. Oh, where'd it go? This one. For the automatic differentiation on Warp, is it necessary to have target functions that are L2 continuous? And do we get the adjoint graph as well to back, propagate, and debug?
Yeah, so it's not required that the target functions are continuous. We're not doing like symbolic differentiation, which might require something like that. So you can have min max, you can have clamps in there, but what that means is that your gradients might end up being noisy, right? And so we see this in contact, especially in contact simulation problems, right? But just like with things like ReLU activation functions as well. We can compute gradients. Whether or not they're useful is like another huge question, but we don't impose any constraints on whether they're smooth or not. The second part of the question is a really good one, because debugging backprop is super painful, right? When gradients go wrong, it's really hard to figure out why. And we actually have a lot of nice tools now to validate against finite differencing. We have a mode where you can dump out the entire computational graph as like a figure, basically like a SVG of the gradient flow, and you can check edges, which edges are not connected properly. So yeah, we are building and also like common problems, like when you overwrite an initial or previous result later on. All these things we've started building quite a lot of like debug tools about. Yeah, I can probably drop a link in the chat to some of those after.
Amazing. Okay, and also before we leave this screen, because this is definitely a technical kind of follow-up question, what are the best practices for debugging Warp code? What do you advise there? Yeah,
so debugging has also got quite a lot better recently. So you can set like WP config debug mode equals debug. And then we'll include things like line information, debugging symbols into all the executable code. And I think with that, you can essentially like correlate Python source code down to the PTEX level if you want to. Another really common way to debug is to run on the CPU. And so with CPU, you can attach like Visual Studio. You can run through in like single-threaded mode and step through all the generated code as well. So that's a really like convenient way to debug, just to switch the device to CPU, where it's a little bit easier to inspect.
Amazing. Okay, cool. And if we didn't hit your technical question, we're going to circle back at the end too. But we want to also make sure we hit some of these use cases for people, because I think some of this is going to be very inspiring for the developers watching. So Mohammed, we're showing your screen now, so take it away.
Amazing. Yeah, thank you. The 10 million download is indicative that people, and like 1 million download per month, indicative that people are actually using it. And when we engage and start talking with the developer community, we realize that the use cases are very broad. They are concentrated around a few basically themes, but they're very diverse, which is very interesting. And as we see these use cases and we get feedback from the community, that's actually inform what we're going to build next on the roadmap. One of the areas that we see most Warp used a lot for is geometry and data processing. Miles talked about a lot of the data structures and primitives, simulation primitives that Warp has. People are using them. They can run those data structures and basically run fast queries in GPU, and also do things like raycasting and even in some cases rendering, which I'll talk a little bit about. collision detection, contact. All of these are like geometry problems. And also we've seen a lot in CAE and scientific data visualization, the data processing were being used a lot. Miles also talked about differentiable physics simulation. This is one of the main motivations where we actually, thought that we want to build Warp, and we see more and more as differentiable simulation becomes a more established field, moving from research to production. We see more and more people using it, and especially in the context of physical AI and design optimization, system identification, real-to-sim pipelines, a lot of use cases and the usage of Warp. We've seen people using it for solver development, like computational physics solver development, and things like CFD, structural dynamics solvers, electromagnetic solvers, and PDE type solvers, especially these days in the context of where AI and physics kind of come together in the AI physics field or physics AI field, where we see people are using Warp in conjunction with learning frameworks like JAX and PyTorch to basically, as part of their pipeline, they're not writing everything in Warp, and this is actually what we really want. We want people to use Warp in where it actually has unique value proposition, and that's where we want to express complex logic in these training pipelines, and that's where people could actually move away from tensor programming, go lower to like kernel programming and use Warp. And so we see you see the diversity actually here. So I picked up a few. There's so many, as you can imagine. I picked up a few recent adoptions of Warp in the next few slides. I think the most prominent one that we were also very close with is Newton. Newton is a Linux Foundation project that we announced at GTC 2025, and then launched and released in GTC 2026 in this year, March this year. So this is a Linux Foundation project, an open collaboration between NVIDIA, Google DeepMind, Disney Research, and more recently Toyota Research Institute and Lightwheel, where we come together with the broader community to build the next generation physics framework for robot learning. So we're laser focused on really fast simulation that where GPU is a first class citizen. It's a very modular and extensible framework, so people can actually extend it with different type of solvers and with different types of collision pipelines and sensors and actuators and things like that. It's highly robust, so it's very good for building modeling more complex phenomena, and it's like Warp, unique value proposition being good interop with ML or DL frameworks. Newton is also kind of inheriting that. So especially for robot learning applications, reinforcement learning in the context of think about Isaac Lab and evaluation as well. So Newton is similar to Warp, is a pip installable package, open source under Apache 2.0. I tried to capture a few key features of Newton as might be very interesting to a robotics and physical AI audience. So Newton supports Majoko Warp, which is already Majoko has a very well-established user base in the robotics industry. Majoko Warp is a GPU accelerated version of Majoko using Warp, and it's used as leveraged as a solver, a physics solver within Newton framework. You have other type of reduced coordinate solver like Featherstone and maximal coordinate solvers like Camino and VBD. And these rigid body, these are like very good for modeling rigid body interactions, for dexterous manipulation, for locomotion scenarios. Here you will see like an in-hand manipulation of a cube in Isaac Lab 3.0, where Newton is a physics backend. One of the key features of Newton is multiphysics, and the fact that you can now go beyond rigid body and simulate more complex phenomena. Granular material, you want a cable or a rod. Think about a cloth, like a thin shell. or elastic solids, or a combination of them. So Newton is flexible enough to allow you to model them appropriately and implicitly couple the simulation in a very neat way. And great news, then Isaac Lab 3.0, which will be GA very soon, these multi-physics features are also exposed. We talked about differentiable simulation. Miles talked about the fact that you can have a auto-differentiable kernel, but whether or not that differentiation is usable, it depends on the phenomena that you're trying to model and capture. So if you're capturing a discrete phenomena like contact, there needs to be a lot of intricate handling of that computation. So just the end-to-end autodiff will not give you a usable gradient that you could use in backprop from. That's why you see that things in Newton are not automatically, like, everything is not like, all the solvers are not differentiable. We're actually taking a lot of care in making sure what we release as a differentiable feature within Newton is kind of really well done, and it provides you usable gradients. So you could use it in system identification techniques and optimization techniques. And one of some of the solvers are already differentiable, but one of the things that is widely requested is Mujoko Warp. We want Mujoko Warp to be differentiable because it's widely used, and we started doing that in collaboration with Google DeepMind, and very soon we're going to have it released. I'm really excited about that. And as we move forward, we will have other solvers and other collision pipelines also being differentiable. So you could use an end-to-end simulation pipeline, not automatically, but differentiable, I would say. And so this is something we care a lot about, and we've heard a lot from the community about as well. Another key aspects of Newton is collision and contact pipeline. Newton has a modular collision pipeline where you could actually select the collision path you want to take, depending on the shape you have you brought to the simulation, whether analytical or discretized. Newton has a way of using SDF or BVH to run the collision detection stages like broad phase and narrow phase. And it also has a very interesting feature called hydroelastic contact, which is kind of inspired by what TRI innovated with Drake. And so this is on GPU implementation of that, you can imagine. And it could be very useful for when you want to simulate tactile sensor, because it kind of doesn't assume that everything is like point contact. It kind of assumes a kind of a surface for your contact. So it would give you a better geometric representation of your contact. Great for tactile simulation modeling. All that to say, Newton is as one of the prime examples, open source, of how you can write physics simulation code, geometry processing code, differentiable code in Warp. So if you're interested to know how you can write your solver or the collision pipeline in Warp, you can look at Newton, use Newton, or if you want to extend it, you can extend Newton, or even you can actually get inspiration from it and build your own physics framework for the application. Let's say you want to do a CFD simulation or something like that. So I touched on renderer. One of the interesting feature in Newton Physics Engine is a tile camera sensor, which is basically a tiled renderer, raycaster that allows you to render with a really fast speed, but maybe lower kind of fidelity, lower feature set, your environment. And this is very useful in, when you want to kind of of course, you have RTX and other renderers that you would use for high fidelity rendering, global illumination and all that. But if you were to if you want to go to the next step in terms of speed, and also you want to run your rendering on CUDA cores, and basically CUDA graph capture your entire computation, using this renderer would enable you to do that. So you would run your physics in Warp, you would also run your renderer in Warp, and then you can actually capture that all in CUDA graph, and that could actually bring you a level up in the optimization. So one of our partners, Flexion, robotics company, used that in a perceptive locomotion scenario, and they've seen huge speed ups compared to Isaac Lab 2.x, like with Isaac Lab 3.x, where this feature is available, both faster and more memory efficient. Of course, there are less feature set, but it will allow you to run CUDA cores on DGX type hardware like H200 or G200, V200, sorry. Another example, recent kind of adoption from into robotics and physical AI world from gray matter robotics. So they are using robots to do autonomous commissioning, and basically using cameras to take pictures and videos of the parts, any parts, without any prior information, and then reconstruct them in simulation. And so this makes virtual commissioning very easy and autonomous. They're using Warp for raycasting and scan post scoring in real time. So they could do that actually in real time, all the processing. And then they use Isaac Lab and Isaac Sim for vision and force sensor physics of the robot cell. So what they essentially do, they find the best pose of the recipe or pose for the robot to basically capture the entirety of the geometry, and so then they can reconstruct it. Very exciting development. Another in a completely different domain, which is close to NVIDIA. This is also Alchemy, one of our partners in semiconductor manufacturing, is using Warp in embedding Warp and shipping Warp with one of their applications that is for process emulation. So this is a process that basically they go through before manufacturing the wafers. So in order to find the right recipes, all the right parameters of the temperature, in order to find all those recipes to manufacture the wafer, they would actually run these simulations previously with TCAT simulation, really long, taking a lot of time. And now they're mixing AI physics with AI and physics to basically build these process simulation much faster. Their application called Altsphere, if I'm not mistaken, and then they actually were able to, using Warp for the emulation part, they were able to process 850x faster what they were previously doing on CPU. And so we are very excited about it. Alchemy is going to deploy the software to many users in the semiconductor domain, so it has a high impact in general in the semiconductor and EDA industry, which is very, very exciting about. One of the other adoptions by Synopsys, which is this, everybody knows, like Synopsys, Ansys, CAE-ISV, software vendor. They've been many years of experience building like engineering grade physics solvers, pre-processing, post-processing AI physics solutions. They have been using Warp and a new library that we recently released based on Warp, which is called Warp Sim Data. Very exciting. I want to shout out to the team who really worked hard to basically purpose-build this library that builds upon Warp. You can think of like Newton as a library or framework built on Warp for robotics. Warp Sim Data is a library built on Warp for processing scientific data, CAE type data, large in memory with supporting different type of formats. And huge speed ups compared to CPU. This is an example where Synopsys is using Warp Sim Data for visualizing an already solved simulation in real time for bottle filling. So there's a lot of fluid interaction with the bottle, and so I believe this is actually they've used agentic solutions to build this example with Omniverse libraries like RTX, OVRTX, and some other, plus Warp and Warp Sim Data, which is very exciting, and how actually demonstrate that how fast we're moving with agentic solutions, and how libraries are becoming more and more important for building the next generations of software solutions, especially in simulation. Another early example is that, like, we have an ongoing collaboration with Autodesk Research. They have a lot of exciting research and development into AI physics and basically next generation of fluid solvers. And so they've built an accelerated lattice Boltzmann CFD solver. You'll see an example of lid-driven cavity flow standard simulation kind of example, but at a very high resolution, 134 million cells. And they've run it on GB200 with Warp, and they've run it on GH200 on Warp, and then GH200 with Fluid X3D, which is OpenCL, and Warp actually plays very closely to that. They also have a JAX backend where they've actually expressed everything, all the physics in JAX, and they compared it, and Warp actually became 8x faster than the JAX implementation. So what they've done, basically, they've used Warp as an alternative physics backend, alternative backend for physics, where they still use JAX for their machine learning algorithms, but they keep the physics code with the Warp backend, and that's how they can get a lot of speed ups. Very exciting.
It's wild to see these great companies doing great work.
Absolutely. Another, one of the kind of, I would say, organic adoptions that I'm really excited about, a company called Velox Sim picked up Warp and start innovating with it, and they built a really engineer grade, like high fidelity DEM solutions, so non-smooth DEM, PBF, and other like types of DEM solutions, and kind of opening new doors in robot learning, but also other fields like heavy equipment, mining. Very excited about what they've done, and like they've gone like 100x speed up when they used Warp for simulating things like a vehicle going over a deformable terrain. So in this case, you do not need to do any tricks, or do any special handling. You just simulate the particles and tune the particles for the right material, and you can get the material identified from real experiments, like mining experiments and real data. So simulation becomes actually a very quick modeling thing, and then you would just need to tune it right based on real data. So makes these type of really complex machine soil interaction simulation easy. The hopper discharge is another example. Rotating drum mixing, kind of a standard example that you can demonstrate. Velox Sim, check them out. They're part of NVIDIA Inception as well. One example that's in a geometry processing side of things, C Infinity is building an application called AutoAssembler, and they have kind of this spatial intelligence engine within it where they could basically find assembly instructions from really complex CAD geometries. So things with like millions of triangles. And so in order to do contact detection, interference, clearance relationship computation between all these like parts, hundreds and thousands of parts, they actually need to run a lot of geometry queries, SDFs and BVH and as such. And then they've used actually Warp, and they've demonstrated that consistently with Warp outperforms existing frameworks that are CPU based by huge margins. Like in the case of this Rover V8 engine, which has around 9.5 million triangles, it takes Warp 1 second to find pairwise relationships, which is insane. To find basically a liaison graph of all the parts, relationship between different parts. And they've done this kind of comparison with FCL and Embry on CPU. Very exciting. One of the last things I want to talk about is one of the things we've been really blessed with is how much the academic and research field community have actually picked up Warp. I'm going to show you a slide of like some metrics, but this is one of the very recent ones, our collaboration with the University of Waterloo Faculty of Mathematics. They're building like the next generation PDE framework that combines really like build high order type PDE solvers, and they've chosen Warp to do that. So this has broad applicability across different physics domains because they're actually solving at a more, I would say, a lower level, writing the PDE framework so they can write solvers like for fluid dynamics and structures and all sorts of other problems that you can express and solve with PDE, partial differential equations. So they've chosen Warp, and they've told us that this has been a game changer for them. It's a very recent, actually, and so they've done really complex things with Warp, and they're planning actually to integrate this in their library called PDE Lite. Very excited about that. And this is a kind of a landscape. Since like Miles gave you a kind of beginning story, 2021 around, we had 2 publications. Today we have 122 peer-reviewed publications that use Warp, and they actually talk about it, because if a researcher talks about a framework that they've used, it means that it really changed their life. Otherwise they would have mentioned it. And so we've seen this across different fields, from multi-body dynamics, geometry processing, cloth simulation, structural dynamics, CFD, and across the world, from US, Europe, Asia. So something we're really proud of, and we really put a lot of emphasis in collaborating with research as well as industry. So I wanted to give a shout out to all our partners and all the community. Yeah.
That's fantastic. So cool. I want to circle back because I'm sure there are lots of information throughout from both of you. But I'm sure one of the questions people have, and Miles flagged this a little earlier, so I'm sure a couple people probably thinking the same thing. This came from Hendrik. Where do you see the border between Warp and Newton physics? I remember that the Warp docs used to have some nice soft robotics examples, which disappeared in robotics switching towards Newton. I don't think it's really picked up again. So I was wondering if that would still fit in better with Warp. What do you guys say to that?
You want me to take this one, Mo?
Yeah, go ahead.
Yeah. So it's a good question, because originally, I mentioned there were 3 main modules for Warp, right? And originally there were 4. One was called warp.sim, and warp.sim was everything that was specific to robotics. So kinematics, fluid dynamics, and contact, friction, rigid bodies. WarpSim turned out to be so useful that it deserved to be its own product, right? And WarpSim basically became Newton. And so everything that was in WarpSim is now in Newton, plus a lot more with Majoko and things like that. I'm pretty sure we picked up most of the soft body examples. If some didn't make it, like, let us know which ones. But we definitely have a bunch of soft robotics examples now, including like some of the differentiable soft robots as well. So for robotics, Newton is really where we're putting all our effort, but everything we do there is built on Warp. So like all the kernels are written in Warp. And so it was a bit of an evolution from WarpSim into Newton.
And Miles just mentioned to let the team know if you're finding something didn't make it through. The best place to get in touch with the team is on GitHub issues, right? I think that's where the team hangs out most of the day.
Yeah.
So that's the best place to go. If you want to talk to other users, other developers in the community, other companies that are using it, the Omniverse Discord server is great for that. But if you want to talk to official team, development team, leverage the GitHub page, which is increasingly the best place to go for most of our tech stack. I'm showing a nice screen here with recap. So anybody has any questions on this? We do have a few. I want to bring Boomy back because I know we have a few questions that were starred here. Let me bring Boomy back here.
Edmar, while you're bringing Boomy,
yes.
I want to add something to what Miles said. One of the great things about Newton is its extensibility and modularity. So, and as soon as you want to extend Newton or write something custom in Newton, you need to write a Warp kernel. So everything in Newton is Warp. So if you're writing something with Newton, first of all, you're using Warp indirectly, but then as soon as you want to customize it, you're using Warp directly, and that's also how you can think about it. So the border is very very thin, but Newton is a standalone package.
Okay, super helpful. And so we do have a bunch of questions. I know we have lots of people watching right now, which is fantastic. If you're catching this, if you missed the first half or jumped in anywhere in between, this is available right away on our YouTube channel, so people can watch it right afterwards, and watch a replay it and slow it down and pause on different screens. All right, so here's where it gets a little fun. Boomi, I'll give you a chance to talk too about next steps with people. Where do they go for resources? And then while Boomi's kind of going over that, Miles and Mo, what would be super helpful, take a look at the starred questions. You should see them in the upper right. I'm going to ask you to kind of, when Boomi's done, you guys can start going through and pick the ones you think are the most relevant that you'd like to talk about really quickly, as opposed to me picking some out that maybe missed the mark a little bit on what we have time for. So, but Boomi, take it away. Let me know if you want to keep this on the screen or you wanted to share something else.
Yeah, we can keep this on the screen, but really quick. So to summarize what Mohammed and Miles did, right? Miles showed the roadmap, what's coming in the future, where Warp started, really the history of everything, and Mohammed showed some of the use cases. We have so many more use cases which we were not able to cover today. Like there's another partner named Universal AGI. They use Warp for like maritime safety. We will highlight it in the future and so on. But if you want to just have everything related to Warp and keep yourself updated, you can go to the Warp web page is the place to go to. And then all of these things that we're showing here, Warp web page has a journey from there as well. So you could go and access everything from the Warp web page itself is what I wanted to cover here, really. And amazing questions, really good collaboration from the community, like so much engagement. It's so amazing to see everyone's so excited about Warp.
Yeah, me too. It's so great. I great to see some new users here in the chat, and some veterans alike. Let's do this. So go ahead and Miles or Mo, if you guys you start saying one of the questions out loud you want to take, and I'll look for it and put it on the screen for everybody.
Yeah, I think a lot of great questions. I think one that I see coming up a couple of times is about like zero copy interop, like who owns the memory when you're passing it off between the frameworks. So yeah, this is a common kind of failure case where things can go wrong, right? And so, whenever you're dealing with raw pointers, things can kind of go wrong. And so we follow mostly Python semantics here, like Python objects, and the GC owns the underlying memory. But it's up to you to make sure that you have some object around to like hold on to that memory so it doesn't just go away. We do put a lot of effort into making sure that stream synchronization works correctly. So when you like run some kernel on a stream, it's not accessing something that was deleted by another framework. So I think we do pretty much as good a job as you can do when you're dealing with raw pointers. But yeah, just something to watch out for sure.
Okay, that's great. And I see a great slide here with some talks, two of them from Miles. And these are coming from GTC. And the NVIDIA On Demand website in general is a great place to go for any sessions from CGraph or GTC. So definitely leverage that. Those are all free. But these ones in particular, you can just scan that QR code and bring it right there. Let us know if you have a hard time finding anything. We'll put a link a little bit later where you can chat with me and the rest of the community team on our Discord server. Okay, so what other question excites you guys?
Yeah.
There's one which is about like hardware prerequisites for CFT with Warp. It would be good to give guidance to the community around that.
Yeah.
Let me show that one right here. Okay, there we go.
Okay, so this is an incredible presentation of NVIDIA Warp, given its amazing ability to accelerate computational engineering and robotic workloads. I would love to know how efficiently this framework handles real-time sensor integration and feedback loops in industrial robotics applications. Also, what are the primary hardware prerequisites for scaling the CFD and physics-based simulations smoothly in a production environment? Thank you for sharing such valuable insights. Thank you for that. A great question, Bilal. So what do you guys say to this one?
So I think there are two aspects to this question. One is the real-time applications, in general, like sensor or not. And what Miles talked about, when Miles talked about deployment workflows, this is actually fits there. So when you can, that workflow within Warp allows you to still continue authoring your programs, Warp programs, complicated or not, in Python with Warp language. And then when you get to deployment, you can actually deploy them to a non-Python environment where you have deployment or real-time criteria. And basically, that's our solution to deployment or real-time systems in general. So that could be a Jetson, or it could be any other kind of hardware where you could run that a real-time application. Miles, do you have anything to add to that real-time factor?
No, I think that all makes sense. That's the deployment angle for Warp, and I think when you come to integration, that's where Omniverse comes in, right? So actually integrating the simulation with multiple components into one, system, whether it's things like FMI, usually you've got some PLC controllers in there as well that you need to connect to your simulation. And that's sort of one level up the stack where Omniverse can help to describe like the entire system.
Yeah.
Amazing.
And one other important portion of the question was about CFD in general, like large CFD solutions, where maybe the throughput is not necessarily a bottleneck, but the amount of memory it requires, to capture. So out of core simulation becomes important. So I'll share a blog we've done actually with the Autodesk research team, where they've actually tried to distribute the Warp-based XLB on 8 GH200 nodes, if I remember correctly. And so they've done the handling of the distribution outside Warp, I think using MPI or some other methods and libraries. But in general, I think Miles can speak to better about like how we think about distribution, basically from multiple nodes, multiple GPUs, and also out of core in general.
Yeah, so we do have integrations with Warp into MPI, and we have some preliminary integrations with things like Nickel as well. So NCCL, which is a very popular, NVIDIA library. Those approaches are quite maybe manual sort of distribution. Then there are approaches with JAX, which can help, automate some of that distribution. But in terms of the hardware requirements, I mean, it's like Mohammed said, really up to the scale that you're looking for. Warp will run on anything from a 30X series GPU upwards. So we don't impose, any real hardware requirements ourselves. It really just depends, the scale of the problem you want to work on.
Amazing. Okay, cool. And thanks to Amelia for putting up that blog that was just referenced. And if you're watching this, you can go and check the live chat, and the link is there. We're putting it on screen for everybody as well. Okay, great. You guys see any more questions here you want to take?
Yeah. There's one that interesting actually from Mohammed. Oh, no, you're asking me. Sorry. So, how Warp can accelerate RL model training in Isaac Lab environment dealing with big number of collisions? Let me see who asked this. This is Afghani, I think. Yeah, amazing. So one of the things I wanted to talk about here is Isaac Lab integration with Warp and Isaac Sim and in general Omniverse applications and libraries. So Isaac Lab Isaac Lab 3.0 has Newton as a physics backend. It exposes also Newton's tile camera sensor, which is also a high throughput renderer that I talked about a little. But more importantly, it also uses Warp as a kind of a front end in addition to PyTorch. So if you want to write observation functions and rewards and things like that that are outside your training loop, you could actually use Warp for authoring them. So directly using Warp kernel. So using Warp as a kernel programming within Isaac Lab. Same applies for Isaac Sim. Isaac Sim also today, like 6.0, ships with as a kind of an Omniverse application. It ships with Warp automatically. In any Omniverse application, Warp is actually come out of the box. But so if you want to use Warp in the context of Isaac Sim, that's also what you can do. I just wanted to highlight that both Warp and Newton are independently kind of exposed in Isaac Lab, which is relevant to this question, I hope.
Great. Thank you for that. And sorry that the question covers up your webcam there when you're talking. I wish I could switch with you. That would be covered. But okay, I see a question from Omniverse Ambassador Scott Dempsey. I had asked him earlier, actually, because I know he's a big fan. I said, hey, you got a question you want to challenge Miles and the team with? So this is what he sent in. What would the team advise for higher function? This is a reinforcement learning use case, not an engineering use case. Thanks for all the hard work. Warp is incredible.
Yeah, this is a good question for Newton, I think. And so for Newton, it's a pretty nice architecture where, we really separate collision detection from the solver. And so you can run collision detection, get out your contact points on the tire with the ground, and the relative velocity, the normal, etc. From that, you can plug those contacts into a Warp kernel that might implement some custom tire model. And I'm not an expert in tire modeling, but I assume it would be some kind of compliant contact model that you can then use to plug forces into your solver, which could be Majoko or it could be one of the other rigid body solvers in Newton. So yeah, I think Newton is a great framework for these kinds of custom modeling problems. And so this was one of the reasons why we started Newton, actually, because with PhysX, it's really hard to extend. You can't go in and just modify the contact model. This is the kind of thing we wanted to enable with Newton because we know there's so many variations, and Warp makes it really easy to go in and customize.
Amazing. Well, thank you, Scott, and thank you, Miles, for that answer. Does anyone see any other questions you want to tackle here?
There was another contact modeling question just around differentiable simulation with discontinuous events like contact and collision. Yeah, this one. And so I sort of touched on it before, but there's no magic bullet to make gradients well behaved. The way we typically approach this is that you have to regularize and soften your contact model. So typically contacts are really hard events, discontinuous events. The way to make them smooth is to add a bit of compliance, make them soft, reduce these hard clamps. So that kind of changes the physical model, but it can make your gradients much better, much more well behaved. We don't do it Warp doesn't do that automatically. It's kind of up to the user how they want to regularize things. But that's typically some of the tricks we would do to make gradients smoother for optimization.
Great. Well, thank you for asking that question. That was great. Okay, any other ones you guys want to tackle? I know we're way over, so I want to thank everyone here and also everyone watching because you've been very much an active participant in this live stream with your great comments and questions throughout. Let me know if the panelists, if anyone here sees any questions you want to tackle before you hit the live stream news section.
Yeah, I think we've covered.
Okay. Okay, cool. So what I'll suggest to everybody who's watching, if we didn't cover an important question or comment that you had, we do have a live stream channel on our Discord server. And I believe we've created a thread specifically on today's live stream. So you can go right there, and myself and Amelia and others from the team will keep an eye on that. And feel free to discuss the content with each other. Or if you want to tag me and ask a question, I can pass it over to one of our great developers here. Well, I can't thank you all enough. I always do this. I should have given you a heads up in the beginning, but I would love to ask each of you what your one big takeaway is that you want people to come away with today, because we covered a lot of ground. I think it's going to be a great resource, a great replay for people who want to learn more about Warp and, of course, Newton. But let me see. I'll start with Boomy. So Boomy, what do you think? What do you want people to definitely remember from today and take away?
Yeah, so Warp is applicable across CAE, EDA, semiconductor, and robotics. There are use cases which we always get surprised with. So if you have use cases outside of these areas, we would love to learn from you. And we would love to highlight you in the next live stream or some other type of engagement that we may have going on. And download more Warp. You could leverage it for your workflow beyond these four that I highlighted as well. That's the main takeaway today.
Amazing. Yeah, we're going to hit the next 10 million soon, I'm sure. And we're
That would
going
be
to
amazing.
we're going to share your work. We love seeing developers post their work on places like LinkedIn. It is very, I'm not saying this lightly. This is very serious. It is very inspiring to the team. We share those internally with each other. We share with excitement. We also look at any challenges or maybe different use cases we hadn't thought of. So it's very helpful. So absolutely share your work on LinkedIn. Feel free to tag me or send me a message. I'm happy to amplify people's great work and add more exposure to the amazing stuff that's happening around the world from developers leveraging this. Okay, you had a couple of seconds to think about it more than Bhumi. Mohammed, what would you like to say? What's your takeaway? What do you want people to come away with this with?
I would say one of the things that I hear a lot from when I talk with developers and users is they think because Warp is Python and then there's also PyTorch and JAX, they always ask about this relationship. So I want to kind of say this, that Warp is there to complement these frameworks because there are things that are, as we said, like awkward to express or inefficient to express in JAX and PyTorch, but we spend a lot of time, have experts in JAX and PyTorch within our team who look at that optimization, who look at the interoperability. So see Warp as a complementary component to those frameworks and not a replacement.
I love it. I love it. Super helpful. Very, very insightful. Miles, last but not least, you started in the dark of dawn. We heard the birds chirping. We're greeting you. Good morning there.
Yeah.
Now the sun is shining.
Sun's up.
Sun is shining. We're gonna let you go and get your coffee. But tell me, what do you want people to take away?
I think probably the main takeaway is that Warp is broadly applicable. You don't have to be into differentiable simulation to use Warp, right? Like that's why it started, but that's certainly not the only thing that you should think about it for. I think anyone who's on the live stream that is using Python will know how slow Python is, right? Python is incredibly slow by default. And so, look for those parts in your pipeline that are, slow, holding you back at the bottleneck. Just think about can you express that as a kernel or as a Warp kernel? I think you'll be really surprised how easy it is actually to get great performance. You honestly don't even have to have a GPU, right? You could run it on the CPU first, and that it also works great. So yeah, just look for those opportunities to accelerate parts of your Python program. I think Warp is a really great tool for that.
Okay, that is very insightful. Also, I'm trying to keep up with some of the questions and comments here. We posted a bunch of links in the chat. Big thanks to Amelia and Bhumi for helping throughout this live stream. And of course, to Miles, Mohammed. I can't thank you all enough. I look forward to the next one. What we'll do now, I'll let the three of you go. I'm going to cover some news slides for people. We have a lot of cool announcements to share, some news and that's going to be relevant to some of what we talked today and other things. But thank you all so much. Really appreciate it. And yeah, we look forward to the next time. So thank you, Bhumi, Miles, Mohammed.
Thanks for having us.
Bye.
Thank you.
Thank you. That was fantastic. All right, 10 million. Now on to the next 10 million. I know we're way over time, so I'll try to go through these new slides really quickly, but there is some really cool stuff. Obviously today we just talked about this 10 million milestone. That QR code will bring you to a nice article about it. And obviously you got the full inside scoop this whole live stream. We took good notes throughout, so we're going to update this description afterwards. We'll timestamp it. I think it's going to be a great resource for developers. Let us know if there are specific topics you want to see covered in the next Warp or Newton live stream, and we'll be sure to do that. Here's a great resource, Getting Started with Newton on the Newton Learning Path. These learning paths are free resources. You can do it at your own pace. Use that QR code to bring you right to the learning path page for this. And give us your feedback or chat with others. If you are really interested and want to talk about this topic and work through it with other people, you could set up your own study group. We have a few active study groups happening. We have a study group that's happened every Wednesday. It's actually starting in 4 minutes if you're watching this live. That is the Isaac Sim and Isaac Lab study group. I'm sure they're going to be talking a lot about this live stream. We also have 2 OpenUSD study groups on Friday. But if you want to do your own study group, let me know. We're happy to help promote and give you resources, information that you need, and potentially speakers to come speak. Some of the study groups happen on our Discord server in the community room, and some of them happen elsewhere. But most of all of them are available virtually, so you can do it from wherever you are. We are very excited about this. Some of my colleagues, Amelia and I, have been just starting to help get things set up for this in terms of the community engagement. But join us at ROSCON in Toronto. Look at that beautiful logo there. That is coming up. We are setting up a WhatsApp group. Actually, it's already been set up. Amelia set it up yesterday. There's a WhatsApp group. So if you're attending ROSCON in Toronto, get in touch with us so we can add you to this WhatsApp group. It's invite only. It's for community attendees to talk to each other before the event, during the event, and afterwards. It's a great place to chat about important sessions or networking events, or grab a coffee. And I think there's a couple of great things happening in terms of coffee meetup as well. So official, like hosted by us. So that's going to be great. Can't wait to hear all about that. How to train a cross-embodiment robot navigation policy with AI agents. There's a QR code for that article. Feel free to, I'm going to keep this on the screen just for 1 second so everybody kind of can take a picture of it. But this is going to be a great article on how to train cross-embodiment robot navigation policy. It's all there on the screen. I don't need to read it. Okay, so I'm going to go to the next slide here. Foundation models for robotics and the physical world. That's Ming Yu, of course. A VP of NVIDIA Cosmos Lab at Fellows Forum on September 24th in Menlo Park, where he'll be delivering a keynote on foundation models for robotics and the physical world. So I hope people can use that QR code and find out all about that, and hopefully you can attend if you're in the area. That's going to be something super exciting to be a part of. Speaking of exciting, shout out to Greer on the GTC team for really spearheading our promotion of this great event, the Golden Ticket for GTC Berlin. You can enter to win the ultimate developer experience at NVIDIA GTC Berlin. It's happening from October 20th to 22nd in Berlin, Germany. Amelia and I will be there. We're really excited. We've got, well, lots of people in the community actually have confirmed that they're attending. We have a WhatsApp group in full swing with those attendees. We also have a WhatsApp channel. We have a Discord channel for GTC Berlin. It's open to everybody, whether you're attending or not, because we're going to share news and announcements on that channel. So feel free to pop in there and say hi. Let us know if you're going so we can add to that WhatsApp group and also invite you to the coffee hours. But this golden ticket contest is your chance to actually submit a project. Tell us about a project and tag one of the NVIDIA folks and other folks from different companies that are looking at these different entries for a chance to win a free conference pass for a GTC and a couple of other great benefits. So hit that QR code for all the details on the golden ticket contest. Super exciting. And as I mentioned, GTC Berlin coming up October 20th to 22nd. That QR code will bring you there. If you are going and you haven't bought your ticket yet, there's a 25% discount that maybe we can paste in the chat. That if you miss it, just ping me. I'll send it to you. You can always find my LinkedIn page by going to edmar.net. That'll give you 25% off the conference pass. And my bet is that this will sell out. So if you're thinking about going, decide sooner than later so you can get your pass, but you can also make your reservations for hotels and travel. As we mentioned earlier, you can chat with the other community members on the specific live stream. So keep the great engagement going that you guys had on the live stream chat. But also, if you watch the replay after the fact, you can go to that this live stream section of our Discord server and just look for the episode. You can see it in the background there. We date them very clearly, so you can find this live stream episode very right away, and then you can jump in the conversation. We always post nice links and stuff there too. So great resource. Thank you, Famar, for generating that QR code. And don't miss out on these awesome study groups. I mentioned them a minute ago. We have 2 OpenUSD ones happening every Friday. One that happens more for the EMEA time zone folks, another one for North America. And we have the one happening actually right now, started 1 minute ago if you're watching live, Isaac Simon Isaac Lab happening on our Discord server. This has been an amazing 90 minutes now. Thank you so much for hanging out a little longer. You are all troopers. You asked some amazing questions and had some amazing comments throughout. I want to thank you all for tuning in today. It makes these live streams fantastic experience for all of us to put together. If this was valuable to you, please like this specific live stream right now. It will really help us know that this is the kind of content you want to see more of, so we can plan other live streams specifically on Newton and Warp, and maybe bring Miles back. So definitely like this. If you get Miles and Mohammed and Boomy back, or maybe others from the team. And also in general, if these live streams are helpful to your work, it's very helpful for us if you could subscribe. Again, it lets other people know that this is great content, and the more we help each other, the further we all go. Thank you so much for tuning in. I will see you on Discord. And if you're going to GTC Berlin, I'll see you not too far ahead there. We're making some great plans there, so I hope to see you there. Otherwise, thank you all for tuning in. And thank you, Amelia, and everyone else to help us put this together today. Until next time, thank you.